Okay, we're picking up with number 7 on the test 4C for AP Stats. It says in number 7, there is a positive association between the number of drownings and ice cream sales. Is the association between these two variables most likely due to causation, confounding, or common response? Justify your answer. So first I looked at causation, and I realized this isn't causation. It's not like eating ice cream is making you drown. That doesn't make any sense. So then I looked at the difference basically between confounding and common response. Confounding would be like if there was some outside variable that was affecting the situation that we weren't able to identify. And common response is some outside variable that we are able to identify that affects both an increase or decrease in both of the variables being described in the problem. And so just kind of thinking about it, if the number of drownings goes up and the number of ice cream sales goes up, why might that happen? And so the answer that I thought of was maybe the temperature. If the temperature goes up, i.e. if it's summertime, there's probably going to be more people out swimming, and thus there's probably going to be more people who end up drowning. And at the same time, if the temperature goes up and it's summer, there's probably going to be more people buying ice cream. There's not very many people that buy ice cream in the middle of the winter. There's not very many people who go swimming in the middle of the winter. So I call this common response because there's a variable that we can find that affects both of the variables talked about in the problem. Looking at number 8, it says a company tests 2 treatments for an illness. The following table shows the outcomes by treatment for each trial. So part A says to calculate the percent of cases that are cured in trial 1 for each treatment, then do likewise for trial 2. So for trial 1, the percent that are cured, there's 40 cases that are cured out of 200 cases. 40 out of 20 is 20%. For treatment B, 30 out of 200 is 15%, so that's the trial 1 data. In the trial 2 data, the percent cured, 85 out of 100, 85%, and 300 out of 400 is 75%. So what I can see from here real quick is just that the treatment A in both trials has a higher percentage. Part B, use the tables above to create a two-way table that shows the relationship between treatment used and treatment outcome. So one side of our table is treatment used. It's going to be whether they use treatment A or treatment B. And the other side, the outcome, whether they're cured or not cured. So I did treatment A and B as my columns, my cure, the outcome, as my rows. So for treatment A, there were 40 cured and 85 cured is a total of 125 cured. And that's out of it's out of 300 because we have 200 total cases and 100 total cases. So 300 minus the 125 gives me 175 cases that weren't cured for treatment A. And then for treatment B, how many were cured? There's 30 from trial 1 and 300 from trial 2. That's 330 total. It's out of 200 and 400. That makes 600. So there were 270 that were not cured for treatment B. Then I just found the totals for each of the rows. There's 300 in treatment A total, 600 in treatment B total. There were 455 total that were cured across both treatments, and 445 that were not cured across both treatments, and 900 people total who were in this study. Part C says to calculate the percent of cases that are cured with each treatment. The percent cured with treatment A is 125 out of 300, which is 41.66. The percent cured for B is 330 out of 600, which is 55%. So right away, I notice up here in Part A, trial A, or treatment A, was higher for each trial. And boom, overall, B is higher. What does that illustrate to me? That illustrates Simpson's paradox. Explain your findings. While treatment A had a higher percent cured in each trial, treatment B had a higher overall percentage cured. This illustrates Simpson's paradox. And that is the end of the test.